Look up at the night sky. What do you see? A canvas of twinkling stars, distant planets, maybe even the faint glow of a passing comet. But beneath that serene beauty lies a universe teeming with secrets so strange, so baffling, that even the brightest minds on Earth can't unravel them. Space isn't just vast, it's enigmatic, a cosmic puzzle box that refuses to give up its answers. And today, we're diving into 25 of its most mind-bending mysteries, a phenomena so peculiar, they defy logic, challenge science, and leave experts scratching their heads in bewilderment. Think about this. We've sent probes to the edge of our solar system, built telescopes that peer billions of light years into the past, and yet the universe keeps surprising us. From stars that vanish without a trace to galaxies that shouldn't exist, from eerie radio signals to cosmic structures so enormous they break our understanding of physics, space is a place where the rules we know seem to twist, bend, or outright shatter. And the deeper we look, the more questions we uncover. So why do these mysteries matter? Because they're not just cosmic curiosities, they're clues to the very fabric of reality. Every unexplained phenomenon is a doorway, a chance to rethink what we know about time, matter, and the forces that shape existence itself, and that's what makes this journey so thrilling. Over the next few minutes, we'll explore these 25 puzzles together, some hauntingly beautiful, others downright unsettling. All of them reminders that the universe is far stranger, far more wondrous than we ever imagined. Ready to have your mind stretched? Let's begin. One night in August 1977, an astronomer named Jerry Amon was scanning the skies with Ohio State University's Big Ear radio telescope when something extraordinary happened. A narrowband radio signal so powerful, so unusual blared from the depths of space for exactly 72 seconds. It was so unexpected, so alien, that Amon circled the data printout in red ink and scribbled a single word next to it: wow. And just like that, the wow signal was born. Here's what makes it so baffling. The signal came from the direction of the constellation Sagittarius, hitting a frequency that scientists had long theorized an extraterrestrial civilization might use the hydrogen line. Natural cosmic phenomena don't behave like this. Stars, quasars, even pulsars have distinct signatures, but the wow signal, it was pristine, artificial seeming, and then gone. Vanished without a trace. Decades of follow-up searches turned up nothing. No repeats, no echoes, no hints of its origin. Some argue it was a rogue comet reflecting sunlight, except comets don't emit concentrated radio waves like that. Others suggest a glitch, but the signal structure was too precise. And then there's the tantalizing possibility. Was it them? A fleeting hello from a civilization far beyond our own? The mystery endures because it defies every easy explanation. No natural source fits, yet the idea of an intentional broadcast lingers like a ghost in the data. To this day, the wow signal stands as space's most haunting maybe, a cosmic whisper that refuses to be forgotten. We know the universe is held together by gravity, planets orbit stars, galaxies spin like cosmic carousels, all bound by this invisible force. But here's the thing, when scientists calculate the mass of galaxies based on the stars and gas we can see, the numbers don't add up, not even close. The math says galaxies should fly apart, their stars scattering into the void, yet they don't. Something out there is gripping them with an unseen hand, bending light, warping space, and refusing to show itself. That something, we call it dark matter. Imagine you're at a party, watching balloons float mysteriously across the room. No strings, no breeze, just motion defying logic. You'd assume something is moving them, even if you can't see it. Dark matter is like that, an invisible culprit leaving gravitational fingerprints everywhere. It makes up roughly 27% of the universe's total mass and energy, outweighing all the stars, planets, and cosmic dust combined. But here's the kicker: despite 80 years of searching, we've never directly caught it. Why is it so elusive? For starters, dark matter doesn't play by the rules of ordinary matter. It doesn't absorb, reflect, or emit light, hence the name. It doesn't clump into planets or stars. It's a ghost slipping through detectors unnoticed. Scientists have tried everything: underground labs shielded from cosmic noise, particle colliders smashing atoms at near light speeds, even telescopes scanning for faint distortions in starlight. All they've found are more questions. Some theories suggest dark matter is made of weakly interacting massive particles, hypothetical entities that barely interact with normal matter except through gravity. Others propose actions, particles so lightweight they're almost ethereal. Then there's the radical idea that dark matter doesn't exist at all, that our understanding of gravity itself is flawed. But every alternative theory crumbles under new observations, leaving dark matter as the least implausible explanation. The stakes couldn't be higher. Crack this mystery and we unlock the blueprint of the cosmos: why galaxies form, how the universe evolved, even its ultimate fate. Until then, dark matter remains the universe's most frustrating paradox. Everywhere and nowhere, undeniable yet invisible, the shadow that shapes the light. If dark matter is the universe's hidden scaffolding, then dark energy is its enigmatic fuel, a force so baffling it makes galaxies flee from one another at ever-increasing speeds. Picture this: you toss a ball into the air, expecting it to slow down and fall back, but instead it accelerates upward, defying gravity's pull. That's precisely what dark energy is doing to the cosmos, pushing galaxies apart faster and faster, as if the universe itself is in a runaway expansion. The discovery came in the late 1990s when two teams of astronomers observed distant supernova, expecting to measure how much the universe's expansion was slowing due to gravity. Instead, they found the opposite: the expansion was speeding up. It was like discovering that a car rolling uphill wasn't just coasting, it was pressing the gas pedal harder with every second. This revelation upended cosmology overnight, earning the researchers a Nobel Prize and leaving physicists scrambling for answers. What makes dark energy so perplexing? For one, it behaves like the opposite of gravity. While gravity pulls matter together, dark energy pushes space itself apart, a kind of anti-gravity woven into the fabric of reality. Einstein once theorized something similar with his cosmological constant, a fudge factor he later called his biggest blunder. Yet here we are, a century later, realizing he might have been onto something after all. The leading explanation: dark energy could be the energy of empty space itself, a property of the quantum vacuum that causes space-time to stretch. But here's the catch: when theorists calculate how strong this energy should be, their predictions overshoot observations by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in scientific history. Alternative ideas abound. Some suggest dark energy is a new kind of field, like the Higgs boson but with repulsive gravity. Others propose it's a sign of extra dimensions leaking into our universe. There's even a radical notion that our patch of the cosmos is a rare, low-density bubble in a far vaster multiverse, making dark energy a fluke of our local environment. The implications are staggering. If dark energy's strength increases over time, it could tear apart galaxies, stars, and eventually atoms in a big rip. If it fades, the universe might collapse in a big crunch, or it might just keep coasting, leaving future civilizations stranded in an ever colder, ever lonelier void. One thing's certain: dark energy isn't just a mystery, it's a ticking clock, forcing us to rethink physics before the answers slip beyond the cosmic horizon. In the vast silence of space, some signals don't whisper, they scream. Fast radio bursts, or FRB, are among the cosmos' most explosive enigmas, flashes of radio waves so intense they outshine entire galaxies for mere milliseconds. Discovered in 2007, these bursts pack more energy than the sun emits in days into a blip shorter than the blink of an eye. And just like that, they're gone, leaving behind a trail of static and a mountain of unanswered questions. What makes FRBs so bewildering? For starters, their unpredictability. Most strike once and vanish like cosmic lightning with no storm, but a handful, less than 3%, repeat, flickering on and off in patterns that defy logic. Take FRB 1211, a burst from 3 billion light-years away that pulses like clockwork every 157 days, or FRB 1810, which erupted 30 times in a single year before falling silent. These repeating bursts aren't just anomalies, they're clues hinting that whatever's causing them isn't a one-time cataclysm, but something persistent. So what's behind these interstellar sirens? The leading suspect, magnetars, neutron stars with magnetic fields so powerful they could strip the electrons from your atoms at 1,000 kilometers away. When these hyper-dense stars quake or snap their magnetic fields like rubber bands, they might unleash FRBs as cosmic distress signals. Some bursts even bear the telltale twist in their radio waves, a fingerprint of extreme magnetism. But not all FRBs fit neatly into this box. Some are too energetic, too clean, too odd to be stellar tantrums, which raises the tantalizing, if controversial, question: could some FRBs be artificial? The idea isn't as far-fetched as it sounds. A civilization advanced enough to power interstellar probes might use focused radio beams, cosmic lighthouses, to navigate or communicate across galaxies. Even Earth's own early radar experiments could, in theory, be mistaken for FRBs by distant observers. Yet the truth remains just out of reach. Every new detection, like FRB 2020 and 6, which traveled 8 billion light-years only to flicker twice in quick succession, deepens the puzzle. Are we listening to the death throes of collapsing stars, the hum of exotic physics, or something far stranger? Until we catch one in the act, FRBs will keep their secrets, reminding us that the universe loves a good mystery. Somewhere beyond the Milky Way starry veil, in a cosmic blind spot we can barely peer through, there's something massive, something hungry. Galaxies, including our own, are being dragged toward it at breakneck speeds, as if the universe itself has tipped sideways and everything is sliding toward a hidden drain. Astronomers call this enigmatic force the Great Attractor, a gravitational monster so powerful it bends the motion of hundreds of thousands of galaxies, and yet we still don't know what it is. The story begins in the 1970s when scientists first noticed something odd. Galaxies in our cosmic neighborhood weren't just drifting apart with the universe's expansion. They were all streaming in the same direction, toward a mysterious point near the constellations Centaurus and Hydra. The pull was unmistakable, as if space had a hidden downhill slope. But when astronomers turned their telescopes toward this region, they hit a wall, literally. The Great Attractor lies behind the Milky Way's zone of avoidance, a thick band of dust, gas, and stars so dense it's like trying to spot a lighthouse through a sandstorm. Here's where things get even stranger. Early estimates suggested the Great Attractor had the mass of tens of thousands of Milky Ways, enough to explain the galactic tug-of-war. But later observations revealed this was just the tip of the iceberg. Behind it lies something far larger, the Laniakea supercluster, a sprawling web of galaxies 500 million light-years across, with the Great Attractor as its gravitational heart. Imagine a whirlpool at the center of an ocean, drawing ships toward it, except the ships are galaxies and the ocean is the observable universe. So what's really lurking there? One theory points to an unimaginably dense knot of dark matter, an invisible anchor warping spacetime itself. Others speculate it could be a colossal cluster of galaxies we simply can't see yet, their light swallowed by the Milky Way's cosmic glare. Then there's the mind-bending possibility that the Great Attractor isn't the final destination at all, that it, too, is being pulled by something even larger and more distant, a structure so vast it defies our current maps of the cosmos. The hunt continues. Infrared telescopes like NASA's WISE probe have pierced parts of the zone of avoidance, revealing ghostly galaxies hidden behind the dust. Each new glimpse raises more questions. Why is the pull so strong? What's behind the Great Attractor's grip? And if we're being dragged toward it, what's waiting for us there? One thing's certain, in the grand tug of war of the cosmos, we're not just players, we're caught in the current. In the constellation Cygnus, nestled among the familiar swirl of the Milky Way, hides a star unlike any other, KSE 8462852, better known as Tabby's star. Named after astronomer Tabitha Boyajian, who first spotted its bizarre behavior, this unassuming speck of light has become one of space's most tantalizing riddles. At first glance, it looks ordinary, a yellow-white star slightly larger and hotter than our Sun. But then you notice the dips. Most stars dim predictably when a planet passes in front. The light drops by a fraction in a smooth, repeating rhythm. Tabby's star doesn't play by those rules. In 2015, data from NASA's Kepler Space Telescope revealed wild, irregular fluctuations, plunges in brightness as deep as 22%, far too extreme for any known planet. Some dips lasted days, others weeks. There was no pattern, no rhythm, just a cosmic flickering that defied every textbook explanation. Theories flew fast. A swarm of comets, maybe, but you'd need millions of them packed impossibly tight to block that much light. A collision of planets, the debris field would have scattered by now. Then came the idea that caught the world's imagination: alien megastructures, specifically a Dyson swarm, vast arrays of solar collectors orbiting the star, harnessing its energy. It wasn't just sci-fi speculation. Even renowned astronomers admitted it was a fringe but plausible answer. After all, if an advanced civilization did build such a thing, this is exactly how it might look from afar. But the cosmos loves to humble us. Follow-up studies found the dimming wasn't uniform. Some wavelengths of light were blocked more than others. That pointed not to solid megastructures, but to fine dust, the kind you'd find in a comet's tail or a planetary collision's aftermath. Except the dust didn't behave like it should. It wasn't warming up like dust normally does when near a star. It was cold, almost invisible in infrared, like a shadow with no source. Even stranger, the star's overall brightness has been dropping for over a century. Old photographic plates revealed it's dimmed by nearly 15% since the 1890s. Stars this mature don't just fade like that, not unless something unprecedented is happening. Maybe it's a vast, uneven dust ring warped by a hidden planet's gravity. Maybe it's the remnants of a shattered moon spiraling into the star in slow motion. Or maybe, just maybe, it's something we haven't even dreamed of yet. Tabby's star refuses to fit into any neat cosmic box. Every explanation solves one puzzle only to clash with another. It's a reminder that the universe still holds phenomena so bizarre they force us to rewrite the rules or consider possibilities that stretch far beyond them. Across the universe, the numbers scream one undeniable truth: we should not be alone. With billions of galaxies, each hosting billions of stars, and countless planets in the habitable zones where life could thrive statistically, the cosmos should be buzzing with civilizations. And yet, when we listen, when we search, we're met with silence. No signals, no visitors, no cosmic neighbors dropping by. This glaring contradiction between probability and reality has a name: the Fermi Paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's a riddle that cuts to the heart of our place in the universe. Let's break it down. Our galaxy alone contains roughly 400 billion stars. Even if only 1 in a million hosted a planet with intelligent life, there should still be thousands of civilizations out there. Some would inevitably be millions of years older than us. With technology so advanced, their presence should be unmistakable. They could build Dyson spheres to harness their star's energy, sending infrared beacons across the cosmos. They might pepper the galaxy with self-replicating probes, spreading like cosmic dandelion seeds. And yet, our telescopes see none of this. The universe appears eerily, unsettlingly empty. So where is everybody? Theories abound, each as fascinating as it is unsettling. The zoo hypothesis suggests advanced civilizations are watching us from afar, deliberately avoiding contact like anthropologists observing an uncontacted tribe. It's a comforting idea until you consider the sheer unlikelihood that every alien society would agree to stay silent. The rare Earth theory counters that maybe we are alone, that the combination of factors needed for complex life, a stable star, a well-placed moon, plate tectonics, even luck is so improbable, Earth is a cosmic fluke. Then there's the darker possibility, the Great Filter. This idea posits that somewhere between the rise of life and the spread of interstellar civilizations, there's a near inescapable bottleneck, a hurdle so deadly, it wipes out intelligences before they can colonize the stars. The terrifying question is whether we've already passed this filter, making us unimaginably lucky, or if it still lies ahead, lurking in our future, nuclear war. Climate collapse, AI rebellion, the filter could be anything, a silent guillotine waiting for civilizations to stumble into it. Perhaps the answer is even stranger. Maybe advanced life inevitably turns inward, creating virtual realities so compelling they lose interest in the physical universe. Or maybe they're here but in forms we can't recognize, an intelligence so alien we're like ants failing to notice a skyscraper. The Fermi Paradox isn't just a puzzle, it's a mirror. Every possible solution reflects back our hopes, fears, and deepest assumptions about intelligence, survival, and our own significance. Until we find proof, or until someone finds us, the silence of the cosmos remains the most profound mystery of all, a question mark hanging over the entirety of existence. Back in the 1970s, humanity took its first bold steps beyond the asteroid belt with the Pioneer 10 and 11 probes, twin pioneers in every sense of the word. These spacecraft were built to last, designed to sail past Jupiter and Saturn, then keep going, carrying messages from Earth into the infinite dark. But as they ventured farther from the Sun, something peculiar happened. An unseen force began tugging at them, slowing them down just a fraction more than physics said they should. This tiny discrepancy, just a billionth of a gravity's pull, became known as the Pioneer Anomaly, a cosmic whisper that defied explanation for decades. At first, the anomaly was easy to dismiss. Space is messy, solar radiation, gravitational tugs from undiscovered asteroids. Even the probe's own aging hardware could have caused the drift. But by the 1990s, the data was undeniable. Both pioneers were decelerating identically, as if caught in some invisible cosmic current. The numbers didn't fit Newton's laws or Einstein's relativity. It was as if the universe had a hidden clause, a footnote in the rules of motion that only applied way out there in the freezing black, the leading theory. Heat not from the sun, but from the probes themselves. Pioneer's radioactive power sources emitted warmth, and its dish-shaped antenna acted like a one-way mirror, bouncing thermal radiation forward. The idea was that this gentle photon push could explain the slowdown, a phenomenon called thermal recoil force. By 2012, a painstaking analysis of decades-old engineering data seemed to confirm it. Case closed, not quite, because here's the catch. Even after accounting for every watt of heat, every possible source of error, some scientists argue the numbers still don't add up. The deceleration was too uniform, too persistent. If thermal radiation was the culprit, why didn't it taper off as the probe's power sources decayed? And why haven't other distant spacecraft like Voyager shown the same effect? The discrepancies are small, almost trivial, but in physics, the smallest cracks can hide the biggest revolutions. Which raises the tantalizing, if controversial, question: could the Pioneer Anomaly be a hint of new physics? Some theorists suggest it might point to modifications in our understanding of gravity itself. ideas like modified Newtonian dynamics or MUND, which propose that gravity behaves differently at extreme distances. Others wonder if dark matter's invisible hand might be at play, subtly tugging on the probes in ways we can't yet model. Or perhaps it's something even stranger, a shadow of extra dimensions, or a quirk in the fabric of spacetime that only reveals itself in the abyss between stars. For now, the anomaly remains a ghost in the data, a reminder that even our most precise instruments can stumble into the unknown. The pioneers may have fallen silent, but their mystery lingers, a testament to the universe's relentless habit of surprising us. And somewhere out there, billions of miles from home, those twin messengers are still drifting, their unexpected deceleration etched into their trajectory like a question mark written in the stars. In October 2017, astronomers spotted something streaking through our solar system that shouldn't have been possible. An object moving so fast, its trajectory could only mean one thing: it wasn't from here. The Pan-STARRS telescope in Hawaii gave it a name that stuck: Oumuamua, Hawaiian for scout or messenger from afar. And what a messenger it was! This cosmic interloper wasn't just the first known visitor from another star system, it was a shape-shifting enigma that refused to fit into any neat category. First, the basics. Oumuamua was small, maybe 100 meters long, but its shape was utterly bizarre. As it tumbled through space, changes in its brightness suggested it wasn't round like an asteroid or fuzzy like a comet. Instead, it was flat, like a pancake or a cigar, depending on who you asked. But the real shock came when astronomers tracked its path. Instead of slowing down as expected under the sun's gravity, Oumuamua sped up slightly, as if pushed by an unseen force. Now, comets do this sometimes. Their icy surfaces heat up, releasing gas that acts like a natural thruster. But Oumuamua had no visible coma, no tail, no classic signs of outgassing. It was dry, dark, and strangely reflective, like metal. So if it wasn't a comet, what was nudging it along? Theories erupted. Maybe it was made of exotic hydrogen ice, vaporizing invisibly in sunlight. Or perhaps radiation pressure from the sun was pushing on its unnaturally thin shape, a cosmic sailboat catching photons instead of wind. Then came the wild-card suggestion from Harvard's Avi Loeb. What if Oumuamua wasn't natural at all? Its acceleration, its unusual shape, its trajectory, could it be debris from an alien civilization or even a derelict probe? The idea ignited controversy, but it wasn't purely fantasy. Humanity has already sent similar objects into space. NASA, a pioneer, placks the Voyager probes, so why couldn't another civilization have done the same? The debate raged and still does. Some scientists point to more mundane explanations, like Oumuamua being a fragment of a Pluto-like planet, sheared off by some ancient collision. Others argue it might be a rare type of dark comet, its outgassing too faint to detect, but the truth is, we'll never know for sure. Oumuamua is already racing out of the solar system, too distant for further study, leaving behind only data and speculation. What makes this mystery endure isn't just the unanswered questions, it's the tantalizing possibility that Oumuamua was a glimpse of something far stranger than we imagined. Whether a shard of an alien world or a relic of another intelligence, it's a reminder that the universe is full of surprises, and sometimes they pass right through our backyard without us ever truly understanding them. For decades, a shadow has lingered in Earth's orbit, a phantom object whispered about in conspiracy circles, debated by astronomers, and shrouded in enough mystery to fuel countless sci-fi plots. They call it the Black Knight satellite, and its story begins not with a modern space telescope, but with a pioneering inventor listening to the cosmos over a century ago. In 1899, Nikola Tesla claimed to have intercepted strange, rhythmic radio signals while experimenting with his Colorado Springs transmitter. He theorized they might be of extraterrestrial origin, possibly from Mars. Decades later, in the 1930s, a Norwegian engineer named Jorgen has picked up similar eerie echoes, delayed radio waves bouncing back to Earth as if something unseen had reflected them. These oddities planted the first seeds of the Black Knight legend, but the myth truly took flight in the 1960s when newspapers reported that the U.S. had detected a mysterious dark satellite orbiting Earth, an object no nation claimed to have launched. Here's where fact and folklore collide. The Black Knight is often described as a 10,000-year-old alien probe silently watching us from polar orbit. Some claim it's visible in grainy NASA photographs, a jagged, asymmetrical shape unlike any human-made satellite. Others insist it's responsible for anomalous radio bursts, even influencing early space missions. But peel back the layers and the truth becomes far more terrestrial yet no less fascinating. The dark satellite of the 60s, it was likely the remnants of Discoverer 5, a failed U.S. spy satellite shrouded in Cold War secrecy. The infamous NASA photo, probably a thermal blanket lost during a spacewalk, its crumpled form catching the light at uncanny angles. As for Tesla's signals, modern scientists suggest he might have been hearing pulsars, neutron stars emitting regular radio pulses decades before their official discovery. Yet skeptics still ask, why does the Black Knight myth persist? Maybe it's the human instinct to find patterns in chaos, or the thrill of imagining we're not alone. Or perhaps it's something deeper, a reminder that even in our own celestial backyard, history's shadows still hold secrets waiting to be uncovered. Whether space junk or something stranger, the Black Knight endures as a testament to our endless fascination with the unknown just overhead. We think of the moon today as a silent, airless world, a dusty museum frozen in time. But turn back the clock 4 billion years and you'd find a place alive with volcanic fury, oceans of magma, and something even more unexpected, a magnetic field. That's right, our moon once had its own protective shield, a force field strong enough to rival Earth's. And here's the kicker, we still don't know how it worked or why it vanished. The evidence comes from ancient moon rocks brought back by Apollo astronauts. Locked inside their glassy surfaces are tiny magnetic imprints, like cosmic fingerprints, proving the moon's crust was once bathed in a global magnetic field. The puzzle: magnetic fields usually require a churning, molten metal core, a dynamo like Earth's, but the moon is too small, its core too puny to have sustained such a powerhouse for long. By all rights, it should have cooled and solidified billions of years ago, yet the rocks tell a different story. One theory points to a cosmic dance. Early in its history, the moon orbited much closer to Earth, and our planet's gravity may have stirred its core like a spoon in molten soup, keeping it active far longer than physics predicts. Others suggest cataclysmic impacts, giant asteroids slamming into the moon, churning its interior with shockwaves that briefly reignited the dynamo. There's even a wild idea that the moon's core was once rich in sulfur, lowering its melting point and allowing it to stay liquid against the odds. But none of these explanations fully fit. If tidal forces from Earth were the engine, why did the field persist even as the moon drifted farther away? If impacts triggered it, why does the magnetism in rocks span hundreds of millions of years, not just brief spikes? And if it was sulfur, why don't modern simulations show a field as strong as the one the moon clearly had? The mystery deepens when you realize how crucial this ancient magnetic shield might have been. Without it, solar winds would have stripped away any faint atmosphere the moon might have had, scouring its surface of volatile elements essential for, well, who knows? Maybe even life. It's a haunting thought. The barren wasteland we see today could have once been a world with rivers of lava, fleeting pools of water, and a magnetic cocoon nurturing who knows what. Now, as new missions like NASA's Artemis program aim to probe the moon's hidden interior, we might finally get answers. Did the moon's core defy the laws of physics? Was its dynamo powered by something we haven't even imagined? Or does this rocky relic hold clues to magnetic fields on other tiny worlds, rewriting what we know about how planets live and die? For now, the Moon's magnetic past remains one of the solar system's most enduring riddles, a ghost of a force that shaped a world, then vanished without a trace. In the sprawling tapestry of the cosmos, where galaxies cluster like cities connected by highways of dark matter, there's a place so empty, so unnervingly vacant, it feels like the universe forgot to fill it in. Meet the Boötes Void, a cosmic sinkhole spanning 330 million light-years, a region so vast you could drop our entire Milky Way into it thousands of times over and still have room to spare. But here's the eerie part. Instead of the usual thousands of galaxies you'd expect in a space this size, the Boötes Void holds maybe 60. That's like wandering into a stadium built for 1 million people and finding only a handful scattered in the stands. How does something this empty even exist? The standard model of cosmology tells us the universe's structure emerged from tiny fluctuations in the early cosmos, a cosmic lottery where denser regions grew into galaxy clusters and emptier ones stretched into voids. But the Boötes Void defies the odds. Simulations suggest voids this large should be vanishingly rare, appearing maybe once in the observable universe. Yet here it is, a cosmic anomaly staring us in the face. Some astronomers call it the Great Nothing, but that undersells its significance. This isn't just empty space, it's a challenge to our understanding of how the universe builds itself. The void's discovery in the 1980s was accidental. Astronomers mapping galaxy distributions kept hitting a dead zone in the constellation Boötes, where telescope after telescope found nothing. At first, they assumed technical glitches were to blame. But as instruments improved, the truth became undeniable. This was no error. The void was real and its implications were profound. If structures like this can form naturally, our models of cosmic inflation, the explosive expansion of the early universe, might need rewriting. Maybe quantum fluctuations in those first moments weren't as uniform as we thought, leaving some patches of spacetime bizarrely barren. Then there's the mystery of the galaxies that do call the void home. These lonely outposts huddle together in thin filaments like survivors clinging to lifeboats in an endless ocean. Stranger still, some appear perfectly normal, with star formation rates and shapes indistinguishable from galaxies in denser regions. How do they thrive without the usual galactic neighbors to interact with? One theory suggests they're ancient relics, forming early before the void stretched to its current size, their gas reservoirs never depleted by the usual cosmic tug of war. Others propose they're interlopers, ejected from busier parts of the universe by gravitational slingshots, but the most mind-bending possibility, the Boötes Void might not be entirely empty. Dark energy's repulsive force could be accelerating its expansion, pushing galaxies apart faster than light can bridge the gaps. If true, future civilizations born inside such voids would see only darkness when peering out, their night skies utterly black, their telescopes blind to the universe beyond. For them, the Milky Way and all its neighbors wouldn't just be distant, they'd be unobservable, erased from their reality by the void's relentless growth. The Boötes Void forces us to confront an uncomfortable truth. The universe we see, the galaxies, the clusters, the webs of light might just be the dense neighborhoods in a far vaster, emptier cosmos. Most of existence could be these silent deserts stretching beyond our vision, rewriting the rules of structure and scale. As we keep mapping the darkness between the stars, who knows what other voids we'll find or what they'll teach us about the fragile architecture of everything. In the vast canvas of cosmic nebulae, where most stellar nurseries bloom in chaotic swirls of gas and dust, one structure stands out like a meticulously crafted jewel, the Red Rectangle Nebula. Located about 2,300 light-years away in the constellation Monoceros, this glowing patch of sky isn't just a marvel of color. It's a geometric oddity that has baffled astronomers since its discovery. Unlike the usual billowing clouds or spherical shells of dying stars, this nebula forms an almost perfect X shape, with crisp, ruler straight lines that look more like a cathedral stained glass than a cosmic explosion. At the heart of this enigma lies a double star system known as HD 44179. These two aging stars orbit so close they're practically dancing on each other's gravity, locked in a cosmic waltz that's sculpting the nebula's bizarre form. Here's how it works. As one star sheds its outer layers in the throes of stellar death, the other star's gravitational pull flings that material outward in opposing jets like water from a spinning lawn sprinkler. Normally, such outflows create messy, asymmetrical shapes, but the red rectangle's precision suggests something far stranger. A pair of dense, dusty rings around the stars, acting like cosmic stencils that funnel the ejected gas into those uncannily sharp angles. What really twists the mystery further is the nebula's color, a deep, rusty red unlike any other in the cosmos. This hue comes from a rare form of carbon-rich molecules called polycyclic aromatic hydrocarbons, or PAH, which fluoresce under ultraviolet light. These aren't just any space chemicals, they're the building blocks of soot, the same stuff in candle smoke and car exhaust. Yet in the red rectangle, they've arranged themselves into a glowing lattice, as if the universe decided to paint with a molecular brush. Theories abound, but none fully explain the nebula's unnatural symmetry. Some suggest magnetic fields are aligning the dust grains into orderly lanes, like iron filings around a magnet. Others propose that the central star's orbital motion is carving the gas into those iconic concentric steps, like a spiraling staircase frozen in time. Then there's the wild card. Could we be seeing light echoes, a trick of perspective where light bounces off nested shells of dust, creating an optical illusion of geometry? Whatever the answer, the red rectangle is more than a celestial curiosity. It's a laboratory for physics at its most extreme. It challenges our assumptions about how stars die, how molecules form in space, and even how order emerges from chaos. And perhaps most hauntingly, it won't last. In a few thousand years, a blink in cosmic time, those crisp lines will dissipate, the red glow will fade, and this fleeting masterpiece will vanish into the interstellar dark. Until then, it stands as a reminder, the universe doesn't just do random. Sometimes, against all odds, it does art. Saturn, the ringed jewel of our solar system, hides one of the most bizarre weather patterns ever discovered. A gargantuan, six-sided storm swirling relentlessly around its north pole. This isn't some fleeting atmospheric quirk. The Saturn hexagon has persisted for at least 40 years, possibly much longer. A geometric freak of nature so precise it looks like it was etched into the planet's atmosphere by some cosmic draftsman. Stretching wider than two Earths stacked side by side, with winds screaming at over 300 kilometers per hour, this colossal polygon defies everything we know about fluid dynamics. So how does a planet, a sphere, no less sport a storm shaped like a stop sign? The answer lies in Saturn's jet streams, rivers of gas racing at different latitudes. On Earth, jet streams meander in wavy paths, creating our ever-changing weather. But Saturn's north pole is locked in a bizarre dance of physics. As the planet's rapid rotation, a day that lasts just 10.5 hours, slams into slower-moving atmospheric layers beneath. It shears the winds into a standing wave pattern. Picture a guitar string pinned at both ends, vibrating at a specific frequency to create a note. Now imagine that note is a hexagon resonating across an entire planet. Here's where things get even weirder. Labs on Earth have tried and failed to recreate this phenomenon. In experiments where scientists spin fluids in tanks to simulate planetary atmospheres, they can produce vortices, waves, even ovals, but never stable polygons. Saturn's hexagon seems to require conditions too extreme for our planet to mimic. A lack of solid landmasses to disrupt airflow, a deeper atmosphere where friction plays out differently, and rotation speeds that would tear Earth's weather systems apart. It's as if the universe reserved this trick for gas giants alone. But the true mystery isn't just the shape, it's the storm's stubborn longevity. Earth's hurricanes dissipate in days or weeks, yet Saturn's hexagon has outlasted every human mission sent to study it. Some theories suggest the storm taps into hidden energy reserves deep within the planet, like a cosmic battery fueling its geometric fury. Others propose it's self-reinforcing, with the hexagon's own winds sculpting the very jet streams that sustain it, a feedback loop frozen in time. Then there's the color. Over decades of observation, the hexagon has shifted from a dull blue-gray to a golden haze, likely due to seasonal changes in sunlight as Saturn slowly orbits the Sun. But even this transformation is puzzling. Why does the hexagon retain its crisp edges while its hue wanders the spectrum? It's a reminder that this isn't just a static shape. It's a living, breathing weather system, evolving in ways we're only beginning to grasp. What makes the Saturn hexagon so captivating is its defiance of expectation. Nature prefers curves, spirals, spheres, arcs, not angles. Yet here, on a world a billion kilometers away, geometry reigns supreme. Whether it's a fleeting alignment or a permanent fixture of Saturn's sky, one thing's certain. This six-sided enigma is teaching us that the universe's playbook for weather is far stranger, far more creative than we ever imagined. And somewhere in its razor-sharp corners, there might be clues waiting to rewrite the rules of planetary science altogether. For decades, dark matter wasn't just a theory, it was the invisible scaffolding holding galaxies together. Every spiral, every elliptical, every cosmic island we'd ever observed seemed to rely on this mysterious substance to explain its structure and motion. That is, until astronomers stumbled upon NGC 1052DF2, a galaxy so bizarre it shouldn't exist. This cosmic oddball, floating some 65 million light-years away in the constellation Cetus, isn't just lacking dark matter, it has none. Zero, nada, and that discovery sent shockwaves through astrophysics, forcing us to rethink how galaxies are born. First, the facts. Discovered in 2018 by a team led by Yale astronomer Pieter van Dokkum, DF2, as it's nicknamed, is an ultra-diffuse galaxy, a wispy, ghostly collection of stars so sparse you could practically see right through it. But when researchers measured the speeds of its star clusters, expecting them to zip around faster than visible matter alone could explain the telltale sign of dark matter's grip, they got a jaw-dropper. The stars moved slowly, lazily, as if nothing invisible was tugging on them at all. Calculations confirmed it. DF2's mass came entirely from its stars and gas. Dark matter, which typically outweighs visible matter 6 to 1 in galaxies, was simply absent. This wasn't just unexpected, it was paradigm-shattering. Dark matter was supposed to be the foundation of galaxy formation, the gravitational glue that pulls gas together to form stars in the first place. Without it, how did DF2's stars even assemble? One radical theory suggests it's a failed galaxy, a cosmic underachiever that somehow stole its stars from another galaxy's outskirts during a long-ago collision. Others propose it's the remnant of a galactic cataclysm, a violent encounter that stripped away its dark matter, leaving behind a skeleton of stars. But here's where it gets stranger. DF2 isn't alone. Since its discovery, astronomers have found a handful of other dark matter-free galaxies, including NGC 1052DF4, DF2's equally baffling sibling. These outliers hint that dark matter might not be as inseparable from galaxies as we thought. Maybe it can be unhitched under the right conditions, torn away by tidal forces during galactic collisions, or perhaps never there to begin with in certain rare environments. The implications are profound. If galaxies can exist without dark matter, does that mean dark matter isn't a fundamental part of their formation, but something that attaches to them later? Or does DF2 prove our theories about dark matter's role are missing a crucial piece? Some researchers argue this discovery actually supports dark matter's existence after all. If it were just a flaw in our gravity equations, why would most galaxies behave as if dark matter is real, while a rare few don't? DF2 forces us to confront an uncomfortable truth. The universe might have more than one recipe for building galaxies. Some follow the standard dark matter playbook, while others, like this cosmic rebel, find another way. It's a reminder that for every rule we think we've uncovered, the cosmos loves to hand us an exception. And in those exceptions, hidden in the faint glow of stars 65 million light-years away, might lie the keys to understanding everything. In the faint glow of the cosmic microwave background, the ancient light left over from the Big Bang, there's a splotch that doesn't belong. It's colder than its surroundings by a few millionths of a degree, an anomaly so slight you'd miss it if you weren't looking. But to cosmologists, this so-called cold spot isn't just a statistical blip, it's a screaming red flag in the data, a cosmic bruise that defies easy explanation. Spanning nearly 2 billion light-years across, this mysterious chill in the universe's earliest light has sparked debates ranging from mundane instrument glitches to the mind-bending possibility of a collision with another universe. First, some context. The cosmic microwave background, or CMB, is often called the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. A glowing fog of hot plasma that stretched across the entire cosmos. Today, we see it as a nearly uniform microwave hum, with tiny temperature fluctuations that reveal the seeds of galaxies and clusters. Most of these variations are small and random, like static on an old TV. But the cold spot, it's like finding a freezer door left ajar in a desert. When astronomers first spotted it in 2004 using NASA WMAP satellite, they assumed it was noise, a hiccup in the data. But subsequent missions, including the ultra-precise Planck telescope, confirmed it was real. The cold spot's temperature dip is too extreme to fit standard models of cosmic inflation, the process that smoothed out the early universe's wrinkles. Simulations show such a feature should appear maybe once in every 50 universes like ours. Yet here it is, staring back at us from the sky. One theory suggests it's a cosmic void, a vast, near-empty region where matter is unusually scarce. In these deserts, light loses energy as it traverses the expanding space, a phenomenon called the integrated Sachs-Wolf effect. But there's a problem. The void required to produce the cold spot's temperature drop would need to be so enormous, billions of light-years wide, that it would dwarf any known structure in the universe. Surveys have found some underdense regions nearby, but nothing on the scale needed to explain the anomaly fully. Then there's the far more radical idea: the cold spot could be evidence of a multiverse. According to some theories of eternal inflation, our universe might be one bubble in a frothing sea of others, each with its own physics. If another bubble universe brushed against ours long ago, the collision could have left a scar, a patch of space where energy drained away like heat leaking through a crack. It's a wild hypothesis, but not untestable. If the cold spot were truly a bruise from another universe, its polarization patterns, the way its light waves are oriented, might carry distinct fingerprints. So far, though, the data remains inconclusive, leaving the door open for skeptics, and skepticism abounds. Some researchers argue the cold spot could be an artifact, a trick of statistics, or an unresolved foreground object casting a shadow. Others propose exotic physics, like dark energy clumping unevenly in the early cosmos. But every explanation comes with caveats, forcing cosmologists to confront an uncomfortable truth. Our best model of the universe, the Lambda-CDM framework, might be missing something fundamental. What makes the cold spot so compelling isn't just its strangeness, it's the way it refuses to fit neatly into our cosmic narrative. Whether a measurement quirk, a gap in our theories, or a window into realities beyond our own, it's a reminder that even the universe's oldest light still holds secrets we've yet to unravel. And until we do, this icy patch on the sky will keep challenging us to look deeper, question harder, and wonder just how much we don't know. Most planets in our solar system spin like tops, their axes tilted just a few degrees. Earth leans at a modest 23 degrees, Mars at 25. But then there's Uranus. This ice giant doesn't just tilt, it rolls, spinning almost completely sideways with an axial tilt of 98 degrees. Imagine a bowling ball knocked onto its side, rolling around the sun like it's doing a cosmic somersault. This bizarre orientation isn't just a curiosity, it reshapes everything about the planet, from its chaotic seasons to its lopsided magnetic field, and it all traces back to one of the solar system's most violent ancient mysteries. The leading theory, a cataclysmic collision. Billions of years ago, when the solar system was a chaotic construction zone of crashing protoplanets, a young Uranus may have been struck by an object twice the size of Earth. The impact would have been so brutal, it could have flipped the planet onto its side, leaving behind a debris field that might explain Uranus's collection of odd, irregular moons. Computer simulations show this scenario is plausible, but here's the catch. If such a collision occurred, why doesn't Uranus show more obvious scars? Its atmosphere lacks the chemical imbalances we'd expect from a planet-sized impact, and its interior heat flow is strangely subdued compared to Neptune, its similarly sized twin. Then there's the magnetic field, another cosmic oddity. While Earth's magnetic field lines up roughly with its rotation axis, Uranus's is a tangled mess, offset by 60 degrees and wildly asymmetric. It's as if someone took a bar magnet and shoved it off-center, then gave it a twist. This lopsided field creates auroras that flicker unpredictably, not at the poles like on Earth, but in erratic splotches across the planet. Some scientists think this chaos stems from Uranus's interior, where extreme pressures may create a slushy layer of electrically conductive water and ammonia, generating magnetic fields in ways we've never seen elsewhere. But the real head-scratcher is the seasons. A single day on Uranus lasts about 17 hours, but thanks to its extreme tilt, each pole spends 84 Earth years in endless sunlight, followed by 84 years in darkness. During the transitions between these extremes, the Sun would appear to loop around Uranus's equator like a tetherball on a string. Yet despite these dramatic shifts, Uranus's atmosphere remains eerily calm compared to Neptune's violent storms. Why doesn't such extreme solar heating and cooling stir up more turbulence? Some speculate its deep, icy layers redistribute heat in ways we don't yet understand, or that the ancient impact somehow stunned the planet's weather systems into submission. Uranus is more than a planetary oddity. It's a time capsule from the solar system's most violent era. Every strange feature, from its sideways spin to its chaotic magnetism, hints at a history written in collisions and chaos. And until we send a dedicated mission to probe its icy depths, this pale blue enigma will keep its secrets locked away, rolling through the darkness on its own peculiar path. Every second, trillions of subatomic particles rain down on Earth, most harmless, some energetic, and a handful so powerful, they carry more punch than a major league fastball packed into a single proton. These are ultra-high-energy cosmic rays, atomic fragments screaming through space at nearly the speed of light, with energies surpassing 100 million billion electron volts. To put that in perspective, that's a macroscopic energy crammed into a particle a quadrillion times smaller than a grain of sand. And here's the kicker: according to everything we know about physics, these particles shouldn't exist. The mystery begins with their sheer power. The most energetic cosmic ray ever detected, nicknamed the "Oh my God" particle by stunned physicists in 1991, packed the kinetic energy of a bowling ball dropped from shoulder height, all in a single proton. That's energies 100 million times beyond what humanity's most powerful particle colliders can produce. But here's the real puzzle: space is not empty. It's filled with cosmic microwave photons, the afterglow of the Big Bang. Particles traveling such vast distances should smash into these photons like cars hitting a fog bank, losing energy long before reaching Earth. Yet these cosmic rays arrive with barely a scratch, as if they've cheated the universe's speed limits. So where do they come from? Most cosmic rays originate within our galaxy, flung toward us by supernova explosions or pulsars. But ultra-high-energy particles are different. Their paths, bent by interstellar magnetic fields, point back to nothing. No nearby supernovas, no active galactic nuclei, no known cosmic accelerators powerful enough to launch them. Some theories suggest they're spat out by supermassive black holes in distant galaxies, their jets acting like natural particle cannons. Others propose they're remnants of cosmic strings, hypothetical defects in spacetime left over from the Big Bang. There's even a fringe idea that they're decay products of super-heavy dark matter particles, annihilating in the halo of our galaxy, but every explanation hits a wall. If black holes are the culprits, why don't we see more cosmic rays from known active galaxies? If it's dark matter, why don't the particles' arrival directions cluster where dark matter is densest? The leading candidate, the Centaurus A galaxy, is too faint to explain the energies observed. It's like finding cannonballs in your backyard with no cannon in sight. Detecting these rays is its own challenge. They're so rare, observatories like the Pierre Auger Array in Argentina use 3,000 square kilometers of detectors just to catch a few per decade. When one strikes Earth's atmosphere, it triggers an avalanche of secondary particles, a sprawling air shower that telescopes can reconstruct like forensic evidence. But even then, the clues are frustratingly sparse. The particles' trajectories are scrambled by galactic magnetic fields, leaving only vague hints of their origins. What makes this mystery so electrifying isn't just the particles themselves, it's what they imply about the universe's hidden extremes. Somewhere out there, nature is running a particle accelerator we can't yet fathom, bending laws we thought were ironclad. Whether it's a new class of object, a flaw in our models, or physics beyond the standard model, one thing's clear: the cosmos still holds accelerators that make our mightiest colliders look like toys. And every ultra-high-energy cosmic ray that streaks through our atmosphere is a postcard from places and powers we've yet to imagine. We think of the universe as a vast, star-studded expanse where galaxies, planets, and nebulae shine like streetlights in the cosmic night. But here's the twist: when astronomers tally up all the normal matter, the stuff that makes up stars, planets, and even us, they come up shockingly short. Half of it is missing. Not dark matter, not exotic particles, just ordinary protons and neutrons, the building blocks of everything we see. This is the missing baryon problem, a cosmic accounting error that's had scientists scratching their heads for decades. The mystery starts with the Big Bang. Based on the universe's earliest light, we can calculate exactly how much normal matter, or baryonic matter, should exist today. But when we count up all the visible stars, galaxies, and gas clouds, the numbers barely scratch 60% of that total. For years, theorists wondered if the missing matter was hiding in black holes, rogue planets, or vast, invisible structures. Then came a breakthrough: the discovery of the warm-hot intergalactic medium, or WIM, a faint, superheated web of gas strung between galaxies like cosmic spider silk. This isn't your average nebula. The WIM is staggeringly diffuse, with temperatures ranging from hundreds of thousands to millions of degrees, and densities so low, a cubic meter might hold just a few particles. It's the universe's attic, stuffed with matter too thin to glow but too hot to ignore. Detecting it requires ingenuity, like using distant quasars as backlights. When their light passes through WIM filaments, certain wavelengths get absorbed, leaving behind chemical fingerprints in the form of faint absorption lines. Over the past decade, telescopes like the European Space Agency's XMM Newton and NASA Chandra have spotted these ghostly signatures, confirming that at least some of the missing matter is indeed floating in these intergalactic threads. But the WIM isn't the whole answer. Even after accounting for it, there's still a gap. About 30% of the universe's baryons remain unaccounted for. Where could they be? One leading theory points to galactic winds, torrents of gas blasted outward by supernova and black hole jets, carrying matter far beyond galaxies' visible edges. Another suggests the missing matter might be tied up in enormous, low-density halos surrounding galaxy clusters, regions so dim they evade even our most sensitive instruments. Then there's the wild card, cosmic rays and neutrinos. These high-energy particles are notoriously hard to track, and while they can't account for all the missing mass, they might chip away at the deficit. Some researchers even speculate that a fraction of the baryons could have been transformed into exotic states of matter under extreme conditions, like quark-gluon plasma in the early universe, leaving behind relics we've yet to detect. What makes this puzzle so compelling isn't just the hunt for invisible gas, it's what it reveals about the universe's structure. The missing baryons aren't lost, they're hidden, woven into the fabric of space-time in ways that challenge our observational limits. Solving this riddle means refining our tools, from next-generation X-ray telescopes to advanced simulations that map the cosmic web in unprecedented detail. And when we finally close the gap, we won't just find a few stray atoms, we'll uncover a new chapter in the story of how the universe organizes itself, one whisper-thin filament at a time. When a star dies, we expect fireworks, a brilliant supernova blast bright enough to outshine entire galaxies, leaving behind either a black hole or a super-dense neutron star. But the universe loves breaking its own rules, and Type Ix supernova are the ultimate cosmic rebels. These bizarre stellar explosions are so weak, they're often called mini-supernova, and the strangest part. Some stars don't just survive them, they come back as zombies, mangled but still burning against all odds. The story starts with white dwarfs, the smoldering cores of dead stars. Normally, if a white dwarf steals enough matter from a companion star, it crosses a critical mass threshold and detonates in a Type Ia supernova, a thermonuclear bomb so uniform, astronomers use them as standard candles to measure cosmic distances. But Type Ix supernova are their fainter, messier siblings. Instead of obliterating the white dwarf completely, these explosions are more like partial detonations, leaving the star's corpse half intact, scorched and battered, but still clinging to existence. Picture a firework that fizzles instead of exploding, leaving the shell behind. Only this shell is a star, still glowing in the wreckage of its own failed death. Why do some stars refuse to die properly? One theory suggests these explosions occur when the white dwarf's ignition is lopsided, with nuclear flames sputtering unevenly through its core. Instead of a full-scale detonation, the star suffers a violent hiccup, a thermonuclear burp that blows off its outer layers without fully disrupting the core. The result is a zombie star, a spectral remnant that's been stripped down to its scorched skeleton, yet somehow keeps shining. The first confirmed survivor, a white dwarf named LP40-65, was spotted still moving at blistering speeds years after its supernova, like a bullet fired from a gun that somehow avoided blowing apart. The implications are staggering. If stars can cheat death like this, our models of stellar evolution might be missing a crucial chapter. Type Ix events account for nearly a third of all white dwarf supernova, meaning these half-finished explosions aren't rare flukes. They're a fundamental part of how stars die. And because they're fainter and less predictable than standard Type Ia blasts, they've likely been masquerading as other cosmic phenomena for decades, skewing our measurements of the universe's expansion. But the real mystery lies in what happens next. Zombie stars like LP40-65 shouldn't technically exist. They've blown off too much mass to sustain fusion, yet they persist, glowing faintly in defiance of every textbook. Some might cool into inert husks over billions of years. Others could reignite if they reclaim stolen gas from their companions, setting the stage for a second, even stranger death. Whatever their fate, these stellar survivors force us to confront an unsettling truth. In the cosmos, even death isn't always permanent, and somewhere out there, a flickering zombie star might be writing a new playbook for how things end. Amid the swirling chaos of spiral galaxies and the shapeless blobs of ellipticals, there's one cosmic oddball that stands out like a celestial bullseye Hoag's object. Discovered in 1950 by astronomer Art Hoag, this enigmatic ring galaxy floats 600 million light-years away in the constellation Serpens, defying every expectation of what a galaxy should look like. At its heart lies a golden yellow core of ancient stars, perfectly encircled by a luminous blue ring of young, hot stars with nothing but utter darkness between them. No spiral arms, no central bar, no messy transitions, just a pristine, symmetrical ring floating like a cosmic halo around its core. It's so geometrically perfect you'd swear it was Photoshop. What makes Hoag's object even more baffling is how it fits, or rather doesn't fit, into our understanding of galactic evolution. Most ring galaxies, like the famous Cartwheel Galaxy, form through colossal collisions where one galaxy punches through another like a bullet through water, sending ripples of star-forming gas outward. But Hoag's object shows no signs of a violent past. No debris, no distorted neighbor, no scars of gravitational turmoil. It's as if this galaxy simply decided to skip the rulebook and assemble itself into pure, undisturbed elegance. Theories abound, but none fully explain this cosmic anomaly. Some suggest it's the aftermath of an ancient merger so perfectly balanced, the chaos cancelled itself out, leaving behind this minimalist masterpiece. Others propose a process called resonant star formation, where gravitational instabilities in a rotating disk funnel gas outward into a ring, igniting new stars while starving the center. There's even a wild idea that Hoag's object is a failed barred spiral, a galaxy where the bar collapsed inward, leaving the outer ring stranded like an abandoned Ferris wheel. But here's where it gets weirder. Peering deeper into the void around Hoag's object, astronomers spotted another, fainter ring galaxy floating even farther back, a cosmic doppelganger. Could this mean ring galaxies form through some unknown, large-scale process we've yet to uncover? Or is it just a freak alignment, a trick of perspective? Every answer only deepens the mystery. What makes Hoag's object so mesmerizing isn't just its beauty. It's the way it challenges our assumptions. Galaxies aren't supposed to look this pristine, this deliberate. Whether it's a relic of forgotten physics, a cosmic collision staged with impossible precision, or something entirely beyond our models, one thing's clear: the universe has a flair for the unexpected. And somewhere out there, in the vast galactic menagerie, Hoag's object keeps spinning, silent and serene, a perfect enigma wrapped in starlight. At the heart of ancient galaxies, quasars are the universe's ultimate powerhouses, supermassive black holes so voracious their feeding frenzies outshine entire galaxies. Normally, these cosmic beacons shine alone, separated by millions of light years. But in 2015, astronomers stumbled upon something that shouldn't exist. Not one, not two, but three quasars locked in a tight-knit dance, a trio so close their gravitational embrace should have ended in a cataclysmic merger billions of years ago. Known as SDSS J0849.5 plus 11144.7, or the impossible quasar triplets for short, this system defies every expectation. Each quasar is powered by a black hole weighing over 100 million suns, crammed into a region just 150,000 light-years across. That's less than twice the width of our Milky Way, a cosmic parking lot where three hyperactive giants are somehow coexisting without collapsing into one. The problem: time. According to our models, black holes this massive and close should spiral together within a few million years, dragged inward by gravitational waves until they collide in a universe-shaking blast. Yet here they sit, seemingly frozen in place, as if physics itself hit the pause button. It's like finding three freight trains parked bumper to bumper on the same track, somehow avoiding collision for eons. So what's keeping them apart? One theory points to their galactic surroundings, a dense nest of gas and stars that might act like cosmic traffic cones, funneling the black holes into stable orbits. Another wild idea suggests these quasars aren't true siblings but temporary illusions, their light bent and magnified by an unseen lens of dark matter in the foreground, creating ghostly duplicates. Yet the data shows all three are distinct, each with its own unique spectrum and redshift. The most tantalizing possibility: we're witnessing a previously unknown phase of galactic evolution, a fleeting moment when ancient galaxies and their black holes clustered far more densely than we thought possible. If true, it could rewrite our timelines for how cosmic structures assemble, hinting at an era when the young universe was a far more crowded, chaotic place. The implications ripple outward. If black hole trios can stall their mergers indefinitely, it might explain why we've never detected the gravitational waves from such colossal collisions. Or perhaps our theories about accretion disks, the swirling maelstroms of gas that feed quasars, are missing a key ingredient that keeps these giants at arm's length. For now, the impossible triplets remain a cosmic paradox, a glaring exception to the rules scribbled in every astronomy textbook. Whether they're rewriting physics or just exposing the gaps in our knowledge, one thing's clear: the universe has a habit of assembling puzzles where we least expect them, and these quarreling quasars are holding the juiciest clues. Deep in the constellation Eridanus, where most telescopes find only scattered galaxies and the occasional quasar, lies one of the universe's most staggering absences, a void so vast it could swallow entire superclusters without a trace. The Eridanus supervoid stretches an almost incomprehensible 1 billion light-years across, a cosmic vacuum so empty it's been dubbed the Giant Nothing. But this isn't just a blank spot on the map, it's a gravitational anomaly, a place where the fabric of space-time itself seems to push matter away. And here's where it gets eerie: this supervoid might hold the key to one of cosmology's greatest puzzles, the cold spot in the cosmic microwave background. The connection starts with gravity. Voids aren't just empty space, they're regions where matter is significantly sparser than average, creating a gravitational tug-of-war. Normally, gravity pulls objects together, but in a void this massive, the lack of matter creates a peculiar effect. Photons passing through it lose energy as they climb out of the void's shallow gravitational well, a phenomenon called the integrated Sachs-Wolf effect. This would explain why the CMB's cold spot, that inexplicably frigid patch in the universe's oldest light, aligns almost perfectly with the Eridanus supervoid's location. It's as if the void's repulsive gravity left a thermal fingerprint on the cosmos's baby picture. Yet controversy lingers. The supervoid's sheer size defies conventional models of cosmic structure. According to standard cosmology, voids this enormous shouldn't exist. They're statistically unlikely to form in a universe where matter is distributed as evenly as our theories predict. Some simulations suggest such a void might appear once in every 1,000 universes. So is this a cosmic fluke or a sign that our understanding of large-scale structure needs revising? Skeptics argue the supervoid isn't empty enough to explain the cold spot's extreme chill. The temperature dip is simply too dramatic for the void's observed depth. Others propose the cold spot might be a stack of smaller voids, their combined effect amplifying the Sachs-Wolf signal, but even that doesn't fully resolve the discrepancy. Which raises the radical alternative: could the supervoid and the cold spot be evidence of something far stranger, like a collision with another universe during cosmic inflation? The debate rages because the stakes are so high. If the Eridanus supervoid is responsible for the cold spot, it would validate our models of how voids sculpt the large-scale universe. But if it's not, if the void is just a red herring, then the cold spot might point to physics beyond our current grasp, from exotic dark energy behavior to wrinkles in space-time left over from the Big Bang. For now, the supervoid remains a tantalizing clue, a cosmic crime scene where the usual suspects don't quite fit the evidence. Whether it's a once-in-a-universe anomaly or a signpost to deeper truths, one thing's clear. In the vast expanse of nothingness, there's still everything left to discover. Imagine a black hole so massive, so powerful, it doesn't just lurk at the center of its galaxy, it escapes. In 2023, the Hubble Space Telescope spotted something unprecedented. A supermassive black hole weighing as much as 20 million suns barreling through intergalactic space at breakneck speeds. But this wasn't just any rogue cosmic heavyweight. It was dragging a bizarre 200,000 light-year long trail of newborn stars behind it, like a celestial bulldozer plowing through the void and leaving a glittering wake in its path. This cosmic fugitive, located in galaxy cluster Abell 785, shouldn't exist under normal circumstances. Supermassive black holes are the anchors of galaxies, their immense gravity holding entire star systems in orbit. So how did this one break free? The answer lies in violence, an ancient galactic collision so cataclysmic it could slingshot even the universe's most monstrous objects into the abyss. Here's the scenario: two galaxies merge, their central black holes spiral inward, locked in a gravitational dance. But when a third galaxy smashes into the mix, chaos ensues. The delicate balance shatters, and one of the black holes gets flung outward like a pebble from a slingshot, ejected at speeds topping 4 million miles per hour. What makes this discovery even more astonishing is the star trail. As the black hole rockets through clouds of intergalactic gas, its gravitational might compresses the material, igniting a shockwave of star formation in its wake. Picture a ship sailing through calm waters, suddenly churning up a frothy, glowing wake, except here, the ship is a gravitational singularity, and the wake is a river of young, blue stars blazing against the darkness. The implications are staggering. If black holes can be ejected like this, it challenges our understanding of galactic evolution. How many other rogue supermassive black holes are drifting unseen between galaxies? Could these cosmic outcasts seed star formation in the void, creating orphaned stellar systems far from any galaxy? And what happens when a runaway black hole barrels into another galaxy? Does it trigger another explosive merger or simply vanish into the chaos? For now, this lone fugitive remains a cosmic anomaly, a glimpse into the universe's most violent dramas. But its very existence proves one thing: even the mightiest forces in the cosmos aren't immune to being uprooted, cast adrift, and forced to carve their own path through the endless dark. Neutrons are the universe's ultimate team players inside atomic nuclei. They bind with protons to form the building blocks of matter, stable and predictable. But strip them away from protons and they become cosmic loners, decaying into other particles in minutes. At least that's what the rules say, because in 2016, physicists spotted something that shattered those rules: a fleeting, ghostly clump of 4 neutrons fused together without a single proton to hold them, a tetraneutron. A particle that, by all known physics, should be impossible. The detection came almost by accident. Scientists at the Riken Research Facility in Japan were firing beams of helium-8 isotopes at a liquid hydrogen target, hoping to study exotic nuclear states. But amid the chaos of collisions, their detectors caught a signature so bizarre it made no sense. An energy spike suggesting 4 neutrons had momentarily stuck together before vanishing. The entire event lasted just 1/1000th of a nanosecond, but that was enough to send shockwaves through nuclear physics. Here's why it's such a headache for the textbooks. Neutrons repel each other fiercely due to the Pauli exclusion principle, which states that identical particles can't occupy the same quantum state simultaneously. Pairing 2 neutrons is unstable enough, but 4, that's like trying to balance 4 magnets all pushing against each other on a tabletop. They should fly apart instantly. Yet the data refused to cooperate. The energy signatures matched predictions for a tetraneutron state. hinting that under extreme conditions, neutrons might briefly overcome their mutual disdain and form an entirely new class of particle. Skeptics were quick to pounce. Maybe it was a measurement error or an optical illusion in the data caused by overlapping signals from other reactions. To settle the debate, teams worldwide raced to recreate the experiment. In 2022, a group at TU Darmstadt in Germany tried smashing lithium-7 and helium-4 nuclei together and saw the same tantalizing signal. Even more compelling, their results suggested the tetraneutron wasn't just a fluke, but a resonance, a quasi-bound state with just enough cohesion to exist for the briefest moment before disintegrating. The implications are staggering. If tetraneutrons are real, even fleetingly, they could rewrite our understanding of nuclear forces. The strong force that binds protons and neutrons might have hidden nuances, allowing for exotic proton-free matter under specific high-energy conditions. Some theorists speculate that tetraneutrons could form naturally in the extreme environments of neutron star mergers or supernova, where densities are so insane, even the universe's stubbornest particles might be forced to cooperate. Then there's the wild card. Could tetraneutrons hint at entirely new states of matter? If neutrons can clump in 4s, why not 6s or 8s? Could there be whole elements made purely of neutrons, lurking in the cosmos where we've never thought to look? It's a tantalizing thread to pull, one that might lead to discoveries far beyond what our current models predict. For now, the tetraneutron remains a phantom, flickering at the edge of detection. But whether it's a quirk of quantum mechanics or a doorway to new physics, one thing's certain: the universe loves to remind us that its rulebook is far from complete. And sometimes the most impossible things are hiding in plain sight, if only we know how to look. From vanishing stars and rogue black holes to ghostly radio whispers and cosmic voids that defy logic, our journey through these 25 space mysteries has been a humbling reminder of how much the universe loves to keep us guessing. Every discovery peels back a layer only to reveal 10 new questions beneath. Dark matter's invisible grip, the eerie silence of the Fermi Paradox, Oumuamua's impossible acceleration, each one challenges the very foundations of what we thought we knew. Consider the implications. We're living in an era where our telescopes can peer back to the dawn of time, yet the cosmos still hides phenomena that make even seasoned astronomers pause. The Saturn hexagon shouldn't exist, but there it spins, a geometric storm laughing at fluid dynamics. The wow signal came and went like a cosmic prank, leaving us decades later still wondering if we were ever meant to hear it. And those zombie stars, they're out there right now, burning against all odds, rewriting the rules of stellar death. But here's the beauty of it: these aren't dead-end puzzles. They're invitations. Every unexplained quirk, every defiant anomaly is a doorway waiting to be kicked open. Maybe you're the person who'll crack the code of the Great Attractor's pull, or finally prove whether dark energy is unraveling spacetime itself. The next big breakthrough could come from a lab, a telescope, or even a YouTube comment sparking an idea no one's dared to voice yet. So keep looking up and keep questioning. Which of these mysteries keeps you awake at night? Drop your favorites in the comments or hit subscribe to join us as we chase the next cosmic head-scratcher. Because the universe isn't just stranger than we imagine, it's stranger than we can imagine. And the adventure, it's only just begun.